Okay, yeah. First thing, let me mention before I do number 8, is back on number 6. Need to correct that one. What was it? Z, yeah, right here, Z. Z should be, this should be right here, 20,725. And so this is going to be the square root of 20,725. And so that takes that out. Those should be 20,725. So you should divide by the square root of 20,725, which only amounts to point. It's a point. It's a 1/10 error. It's 168.8 miles per hour. Check me on that, but I think it should be 168.8. 24,300 divided by the square root. But you know us math people, we just don't like even little bitty errors. Yeah. Okay. Feel better now there. All right, so number 8. We have a swimming pool problem. This is kind of like the trough problem because we've got a swimming pool which has the cross-section area as shown there, but it's 25 feet long. So just imagine, we're going out here 25 feet this way. There's our swimming pool, okay? That's what our swimming pool is going to look like. Okay? I'm going to leave that there. All right. So, if the pool is being filled at a rate of 0.5 feet cubed per minute, how fast is the water level rising when the depth is 3 feet? Okay, well, that's a good question. See if we can answer it. Of course, we're being filled at that rate. So, what does that mean? This rate right here. What does that mean in terms of our calculus terminology? Wouldn't that be, that's the rate of being filled, so that's the rate of change of the volume? So that's dV dt. dV dt is 0.5. feet cubed per minute. How fast is the water level rising when the depth is 3 feet? So here's the thing. I'm going to come up here and I'm going to have, the swimming pool right here is 5 feet. This little jog, if you will, out of it. That's 5 feet tall. So when we're at 3 feet, we're right in here. So I want to know what, when I've got a height there of 3, how fast is that height changing? So dH dt when h is 3. What is it? Well, as you know, the first step after talking about all that is to get a formula. And the volume of this particular part, now if we were up here in the upper part, that'd be another thing, but we're down here. So wouldn't the volume of this part right here be just like it was for the trough in number 7? I'd take the cross-sectional area times the length of the pool. Same formula basically as the trough. Now, the thing about the cross-sectional area here is we're talking about the cross-sectional area of a different sort. I'm talking the area of what is this shape, cross-sectional area here. Isn't that a trapezoid? Trapezoid. And so the trapezoid formula So this cross-sectional area is a trapezoid. Does anybody know right offhand the area formula for a trapezoid? Area formula for a what? Okay, keep going. Different ways you can write it, but it's 1/2 the height times big B plus little b, where by that I mean big B is this distance here, and little b is the distance on the bottom. It's the two, big B plus little b are the two parallel side lengths, if you will, of the trapezoid. So that's, I guess, the bad news. The good news is I've got the length, and the length is going to stay fixed because that length is talking about the length of the pool, which is 25 feet. Right, I said 25. Don't I have 25 feet length of the pool? Yes, 25 feet is the length of the pool. All right. So this is our formula. Now, what are we looking for? We're looking for dH dt. However, this formula has two things other than h and v in it. It's got big B and it's little b. Now, here's also some good news. What about big B? The thing about big B is it's fixed, isn't it? Big B is also fixed, just like the length is. Big B is fixed to be 20 feet. Little b is fixed to be 20 feet. That's not going to change. Even if the water level rises, say, it's at 1 foot, little b is still 20. 2 feet height, little b is still 20. So this just like the length is fixed. So let's make that also a little change there. Big B, though, is not fixed because depending on the height of the water, big B is going to be longer or shorter, right? So big B is a variable. Well, unfortunately, I don't know anything about dB dt, big B dt. And so I have to get, just like I did in the trough problem, I have to replace it in terms of h. I need to get this big B in terms of h. And here's how I can do that. Let's draw that kind of this area here. Explode that out over here a little bit. Okay, where this whole thing is the 5. Okay, but my water level is coming in here, okay, H. That's my H. Okay, and that's my big B. Right there, little b, of course, that's 20. Here's what I'm going to do. I can get big B in terms of H. If you'll notice here, draw a little triangle there at the corner and call this, I don't know, whatever you want to call it. Call this little part here A. And of course we know that big B goes all the way across. And so couldn't we say, and here's something else we know. This part here is 20. Okay. This is H. Don't we know this too? Isn't this 2 feet right here? That'll be significant here in just a second. Okay? So, big B is 20 plus A. Now, what I can do with that is, I'm trying to get big B in terms of H. How can I, though, I've got it in terms of little a, what I call little a, this little piece right here. How could I get A in terms of h? Well, do you see something here? Don't I have a similar triangles just on this little corner triangle there? Can I use my similar triangles again? Wouldn't I have, I could set, I know that A and 2, I'm talking about this triangle here is similar to this big triangle right here. You with me? The little triangle here is similar to the big triangle right there. So don't I have that A is to 2 as the H is to what? Doesn't H go to 5? Because that total height there is 5. With me on that? A is to 2 as H is to 5. Well, if I cross multiply there, 5A equals 2H. Divide by 5, I've got A is 2H over 5. 2H over 5. And so there you go. Substitute that in. We got B is 20 plus 2H over 5. And so that's our big B in terms of H. So let's replace it. It's 1/2 H. So now I know big B is 20 plus 2H over 5. And I've got plus 20, another plus 20 there, times 25 halves. Or times 25, sorry. Did you see what I did there? The thing of these are, on those trough problems, is you've got to get that one variable out of there in terms of the other variable, which in this case is the height. If you've got that extra variable on the right, like we had here, you've got to get that out of there in terms of the other. So that's the whole thing. And usually it is using your similar triangles. This was a little bit of an altered form of that, but okay. All right. So how we're going to clean that up? Well, let's go ahead and put the 25, the 1/2 times the 25 together. So that'd be 25 halves H. And then in the parentheses here, I can add the 20, so I have 40 plus 2H over 5. Now, before I do the derivative there, I think, instead of having to use the product rule, I think it's going to be much nicer if we just go ahead and multiply the 25 halves H in. So we get volume equals 25 halves times 40, 25H times 40, and then 20 plus 25H, 25 halves H times 2H over 5. And simplify that, which I think does nicely. That goes 20, so that's 500H up front. The 2's cancel. The 5 goes into the 25. So don't I have 5H squared there? All right. So finally, here's our volume of our swimming pool, and it's only in terms of H. So now I can set off doing what I intended to do, which was find the rate of change of the height. So I need to, what's next? DDT it? Okay, so the left side is just V, so the DDT of that would be dV dt, or 1 dV dt if you like. Okay? Then, DDT that, that's going to be 500 dH dt. Then the DDT of that would be 10H dH dt. And now we can substitute. What do we know? dV dt, what was dV dt? 0.5 from the problem. 500, well, we're looking for dH dt. So that'll stay in there. And then 10, the height is that we're looking at is find dH dt when h is 3, right? That was 3 feet. Yeah, 3 feet. So d 0.5 equals, that'll be 500, that'll be 30, of course, so it'd be 530 dH dt. So divide by 530. And so that water level rising is not very much. 0.5 divided by 530. Ooh, really small. 0.009, 0.0009433 is dH dt, and that is feet per minute. Is that the time units? Yeah, feet per minute. So yeah, if you've ever filled a swimming pool, you know it doesn't rise very fast. So it's not even a foot per minute there. It's way less than a foot per minute.